Swayam Prabha. Digital India. Educated India.
Welcome to the DTH sponsored course on micromachining. I am going to discuss in this particular lecture on electric discharge micromachining, abbreviated as EDMM. Acknowledgement. Dr. G. Karthikeyan, research scholar at IIT Kanpur, Advanced Machining Processes. Lecture delivered by Professor Vinod Kumar on micro EDM and micro electric discharge machining topic by Professor S.S. Joshi in Introduction to Micromachining book. Organization of the talk: Introduction and working principle of EDM and EDMM, comparison of EDM and EDMM, EDMM machine setup, process parameters and micro tools fabrication, types of EDMM operations, applications of EDMM, and concluding remark. Introduction and working principle of EDMM process. Now here you can see the male and female parts of a, these one which are used in our houses, and you can clearly see here, this is the black carbon, here is the black carbon, and burnout parts are also there, and here. Lazarenko brothers found that female and male parts of an electric switch have craters formed on it, as you can clearly see over here as well as here. They started thinking why it is so. They also raised a question to themselves: can we make constructive use of this destructive activity? If the discharge is submerged in dielectric or liquid, the energy is concentrated into a small area, diameter of discharge or spark will be small. Both brothers studied the phenomena in detail and developed first electro spark machining machine in 43rd attempt. You will be surprised to know that 42 times they failed to develop the desired machine, and in 43rd attempt they got the success, and then they patented it as electro spark machining machine. Later on it was named as electric discharge machining machine. Developed and patented a machine named as electro spark machining machine, later named as electric discharge machining machine. Working principle of EDMM, electric discharge micromachining, and electric discharge machining principle remains the same. So here you can see, this is the tool which is cathode, this is the workpiece which is anode, and inter electrode gap is few hundred micrometer in case of EDM and few tens of micrometer in case of EDMM. Now here is the dielectric, it is the ionized column, as you can see, and once the sparking takes place, there is a crater formed on the cathode as well as crater formed on the anode, and this molten material is flushed out by the flowing dielectric. Now here you can carefully see that material is removed from the tool also, which we really do not want, but it is a characteristic of the process being thermal process. Sparks created deliberately heat in a localized area that depends upon the diameter of the ion column or the spark column. You can see the crater over here. Melting and or vaporization is the main mechanism of removal of material in case of EDM and EDMM. 100 microns of inter-electrode gap is there and few tens of micron of inter-electrode gap in case of EDMM process, and you can see this in this schematic diagram. These are the crater formed over here and here, and this is again dielectric, and this is the column, plasma column, and this is the vaporized dielectric. Spark will melt, vaporize a small amount of material from the tool and workpiece both, and both are acting as electrodes. Micro EDM elements: dielectric, tool, power supply and workpiece. You can see here very small schematic diagram. Servo control is there for the controlling the motion of the tool holder, and here is the tool, and dielectric is there, workpiece is there, same as of EDM. Schematic diagram of electric discharge machining and electric discharge micro machining, it is applicable for both. Here is the RC circuit, this is the resistance, capacitance, this is the tool, workpiece. If you enlarge this part, you will find that tool is here, workpiece is here, and there is the overcut on the workpiece. That means the diameter of this workpiece of the machined cavity is larger than the diameter of the tool, and that is known as overcut. And here in this part where sparking is taking place, you can find the ions are there and electrons are there, electrons and ions both are there, and they form the column, plasma column, and this is the workpiece and crater is being formed. EDM and EDMM, time versus voltage, time versus current, where sparking will take place. This is a circuit that we have just seen already. Here you can see this is the voltage, this is the time here, and this is the building up voltage over there. This is the supply voltage line, and this is the breakdown voltage. As soon as the voltage reaches to the breakdown voltage, sparking takes place, and this is the discharging area. So you can see charging time and discharging time, and once discharging is over, again it starts charging and then discharging time. So this is the voltage variation with time, and current variation with time is shown here. As soon as discharging starts, current starts flowing, and once the discharge is over, then current stops and it becomes 0. Then again it restarts and becomes again 0. Vs is the supply voltage, breakdown voltage is Vv, and Vi is the voltage at any time t, and that is what is shown over here. Now this is important figure to see here. Now this is the tool roughness and this is the workpiece roughness. Wherever there is a minimum gap, there sparking will take place, voltage breakdown will take place, and sparking will take place over here. Now here you can see clearly at two places the gap between the tool and workpiece surface is what is needed or smaller than what is needed. If it is at more than one place, then more than one spark can take place at a time, and that is what is known as multiple spark, EDM and EDMM. However, most of the work that has been done theoretically is on single sparking phenomena. But if this condition is satisfied, multiple sparks may take place at the same time, and in fact in real life it is suggested by many researchers that it is multiple sparking process rather than single sparking process. It clearly indicates that multiple sparks may take place if the conditions for sparking are satisfied, as shown here at A and B. Electrodischarge micromachining is a micromachining technique involving the successor micro sparks of small electrical pulses between a micro tool electrode and workpiece. Here please note it carefully that tool and workpiece materials are to be electrically conductive. Localized breakdown of dielectric resulting in micro discharge. High discharge frequency is required normally, and in EDMM the key factor is to limit the energy in the discharge. A small discharge energy per pulse can be as small as 10 raised to power minus 6 to 10 raised to power minus 7 joules. A small volume removed by one spark, because energy is small, so amount of material removed is also small. Precise micro holes of 15 to 300 micrometer and 0.5 micrometer roughness RA value is normally less than 0.1 micron. Pulsed power supply system. Power supply produces pulsed high frequency electrical spark discharges between the tool electrode and workpiece. EDM power supply also controls the desired gap value. You normally have the AC power supply, you use the rectifier to convert it into DC, then you use the pulse, you convert the DC into the pulse DC. RC pulse generator, RC charging discharging circuit gives low material removal rate, short spark time, improved surface finish and high tool wear rate. Electronic pulse generator, all types of flexibilities are available with electronic pulse generator. For rough machining you use high energy and low frequency pulses, and for finish machining you use low energy and high frequency service. This is true for EDM as well as EDMM. Dielectric fluid, you can use transformer oil, paraffin oil, lubricating oil, and very commonly used is the kerosene oil. In many applications nowadays deionized water is also used for EDM, wire EDM also. It gives high material removal rate, high tool wear rate, corrosive, and give good coolant used in wire EDM. Then one of the main problem is the corrosiveness of deionized water. Purpose of flushing, it removes byproducts from gap, that is the inter-electrode gap. Whatever reaction products are produced, they are removed by flushing of the dielectric, high material removal rate and good surface finish, and avoid short circuits. EDM and EDMM, different methods of dielectric supply. Now these methods, some of these methods are not applicable really speaking for the EDMM. Say in the first case where you are having the hole in the tool, it is not possible because tool itself is of micron size, and to drill a hole, proper hole in that becomes very difficult. So this is more applicable for EDM process, suction through electrode, and second one again this is suction through workpiece. Here you can make the hole in the workpiece, so this is feasible, but here in this particular case pressure through the electrode, again drilling the hole here becomes difficult in case of EDMM process, but applicable for EDM process. And pressure through workpiece is feasible, you can have the hole here and then dielectric will go like this. Now in this particular case jet flushing, you supply from one side and it goes from the other side, and dielectric flows over here for creating the sparks. And then this is the another one, through vibration of electrode, you are supplying it like this and vibrating the electrode so that it goes out. So these are the various methods for dielectric flushing. Now you can see this particular book for details. For EDMM it may be difficult to have micro hole in it, micro tool. In that case other method of dielectric supply has to be chosen. Evolution of the plasma, you can easily see here. This is a tool, dielectric, workpiece, vapor bubble formation is there, and avalanche is there, and avalanche growth is there continuously. Finally, plasma formation is there, and sparking takes place, and you have the gas bubble again, and then again you start from here. You can see the similar thing over here. Pre-breakdown current is there, micro peak is there, and then you have nucleated bubble over here, which is rises in the shape and size, as you can see over here, and it comes to this shape, and finally you have the plasma channel where sparking takes place. So, this is the reference from where it has been taken. So, you can see different phases over here. Spark characteristics. Now, analysis of a spark profile during EDMM process as well as EDM process. In both cases it is applicable. In EDMM it is a much smaller in shape and in size as compared to EDM. Now, tool is there, workpiece is there, representation of the spark region. As you can see, this is the spark shape estimated over there, which is between the tool and workpiece, and here is the dielectric, and certain boundary conditions are shown over here. For theoretical study, spark radius is needed, energy distribution should be known, anode, cathode, dielectric. What is the energy distribution of total spark energy, how much it is going to anode, how much it is going to cathode, how much it is going to dielectric, and if radiation is considered, how much loss is there due to radiation, and then interelectrode gap, how much it is distributed, how it is distributed. So, all this should be known for analysis of the EDMM process, and this is the one which was done by Shankar, Prem Shankar, for EDM process. Again you can see here, this is the cathode, this is the anode, and this is the compressed liquid shock wave, and this is the plasma channel. Evolution of a spark. Now, this is very interesting one. Now, here this was proposed by Prem Shankar and others, and you can see here the spark radius, and this is the distance. So, how it is varying? You can see at 2 microseconds, and this is at 5 microseconds. With time, the shape of this spark is continuously changing and stabilizes after certain microseconds. Say in this particular case, it is stabilizing after about 10 microseconds, that is the last one here, and this is the at the beginning. So, this shows that it is not a fixed shape and size of a spark, rather it is changing with time. Now, you can see here time and spark radius at different locations. Say we had the cathode, we have the anode, and you can see at 1 this is the cathode radius varying with time, and this is the anode radius varying with time 2, and this is the radius of the central plane, and that is varying with time. So, this was studied theoretically by Prem Shankar and others. Now, spark radius, how it is changing with current? Current is major element responsible for spark characteristics. So, you can see here 1, 2, 3, 1 for cathode, 2 for anode, and 3 for central plane. It is continuously increasing 1 and 2 rapidly, but in central plane it is not increasing so rapidly, but it gives the idea that spark radius is continuously changing with time and well as with the current amplitude. Spark energy distribution. Now, the question is where the energy of the spark is going. Once spark energy is there between in the plasma, it is distributed to the workpiece, tool, dielectric, debris, and residual. So, it is conducted away in the workpiece, stored, part of it is stored in the workpiece and used for erosion of the workpiece material, because material is removed from the workpiece, and some part of it is conducted away to the tool, stored in the tool and used in unwanted wear of the tool. Tool wear is also taking place. Then substantial amount of this energy goes to the dielectric, convected away and stored in it, and then debris formed, they also stored certain amount of the spark energy, and some of the energy is residual energy lost by radiation, some energy required for ionization, some energy lost in light, and some energy is lost in the sound. So, this is how the energy distribution takes place in EDM as well as EDMM process. EDM and EDM process is current and frequency of sparking, how current affects crater size in EDM process. You can see here, this is at 1 ampere, very small crater size, but as the current is increasing from 1 to 3 ampere, 4 ampere, the crater size is continuously increasing. This is telling that as the current is increasing, crater size is increasing, so the material removal rate will also increase with current, as we will see it, as well as surface roughness of the surface will also increase with increase in the current. So, how frequency of sparking affects crater size or Ra value in EDM, that also we can see here. At 12 ampere, this is the spark size with single frequency. At 2 frequency, size of the spark is decreasing. As you keep increasing the frequency, crater size keeps on decreasing. Crater size is keeping on decreasing. So, it simply means that surface finish will improve if the frequency of sparking is increased. So, as current increases, Ra value and MRR increase. As frequency of sparking increases, Ru value decreases, as we can see over here. Role of EDM in micromachining. EDM, a controlled metal removal process. Metal removal by means of electric spark, that we have already seen. EDMM can machine any material irrespective of its hardness and other physical properties, provided they are electrically conductive. And another important point is the EDM is non-contact machining process. So, non-contact machining of curved surfaces with high precision, machining of inclined surfaces and thin, difficult to machine surfaces is feasible with EDM and EDMM process. In EDMM, the spark will melt and or vaporize a small amount of material from the tool as well as from the workpiece both. Although we do not want the material removal from the tool, but it is a part of characteristic of the process. A spark produces intense heat with temperature reaching as high as 8000 to 12,000 degree Celsius, which results in melting of almost anything, and this temperature of 8000 to 12,000 was calculated by Mr. Prem Shankar during his research activity. The metal removal process removes or erodes very tiny pieces of metal from the workpiece at a controlled rate, and complex shapes can be machined by EDM as well as EDMM process. Overcut and duty cycle. Here you can see that this is the electrode and this is the machined workpiece. So, whatever is this gap between the two, that is known as overcut, and overcut is obtained in all the cases, whatsoever small it may be, but overcut is always there. So, this is the overcut here in all the three cases. Now, you are going to use these terms in theoretical analysis and experiments also. On time, this is the on time for square pulses, and this is the off time This is the pulse time. On time plus off time becomes the pulse time, and this on time divided by pulse time, that will give you the duty cycle. So, here it is the 60% duty cycle. Kinds of surface layer, another important thing here. When you are machining by EDM and EDMM processes, you will find recast layer is there, which is which normally lies between 2 to 50 micrometer. For extremely hard and brittle material should be removed. Heat affected zone around 25 micrometer. Converted layer, there is a change in grain structure is there, then you call it as converted layer, and then you have the parent material. So, you can see here recast layer, heat affected zone, parent material is there, and here you can see 4 layers. This is the drilled hole, this is the recast layer, this is the heat affected zone, this is the converted layer, and this is the parent material. So, a schematic diagram of 3 kinds of layers on EDM and ED drilling a component. Comparison of EDM and EDMM processes. Comparison of macro EDM and micro EDM based on scaling effects. Now, let us see it carefully. Macro EDM, here you have the dimensions greater than 1 millimeter, while in micro EDM size ranges between less than 1000 micrometer or less than 1 millimeter. Higher material removal rate in case of macro EDM, while relatively lower material removal rate in micro EDM. Higher spark gaps, inter-electrode gap is comparatively much higher in EDM as compared to EDMM process. Very high power consumption and high maximum current rating, high maximum current rating in case of EDM, macro EDM, and relatively very low power consumption in micro EDM. Higher discharge voltage used approximately greater than 80 volts, while relatively lower voltage used normally 10 to 20 volt, and low frequency pulsating discharge current, while here you use very high frequency pulsating discharge current applied to the system. Based on the circuitry elements, you can see here you are using RC relaxation circuit, here using RC single pulse discharge, here single spark process, here also single spark process. Forced mechanism for constant gap voltage current during a spark, single capacitive discharge, no constant voltage and current. User defined pulse on time is not constant in this particular case. Constant current and gap voltage throughout the discharge, variable current and gap voltage during the discharge. EDMM machine setup and setup manufacturer. Machine elements are there. Major elements of EDM machine: power supply, then dielectric system, electrode, tool and workpiece, and then you have the servo system. So, these are the 4 major elements of any EDMM and EDM machines. This we have seen already. Dielectric system and dielectric fluid. Dielectric system has dielectric fluid, reservoir, filter, pump and delivery devices. Filter is very much important because you are recirculating the dielectric, and for that purpose you should very properly filter it out before recirculating it. For recirculation you need the pump. Good dielectric fluid should have high dielectric strength, so that you get higher material removal rate. Minimum ignition delay time, and then minimum deionization time, effective coolant, it should work as effective coolant, and high degree of fluidity. These are the desirable characteristics of the dielectric. Servo system, this is the one, various elements are shown over here. like piezo tube is there, micro EDM circuit is there. Not details are shown over here, it is just a schematic diagram. So, to maintain predetermined gap between the electrodes, because this is very important, sparking will take place only when you control the gap between the tool and workpiece and the dielectric breaks down, then only sparking will take place. Gap bridged by electrically conductive material, signal to servo system to reversed direction. What happens here? This is the tool, this is the workpiece. Now, if the material that has been removed from the workpiece that bridges the gap between the tool and the workpiece, then short circuit will take place. To avoid this short circuit, the signal to servo system is sent, servo system is there, and this servo system will move the tool upward, so that conductive debris, it is flushed out by the dielectric. That is what written here. This system, servo system reciprocates towards and away from the workpiece. It reciprocates the tool towards and away from the workpiece until dielectric flushes out from the gap, that is here. And if insufficient flushing, then very long cycle time, because if insufficient flushing is there, then tool will keep on moving up and down before really sparking takes place. So, it reduces the efficiency of the process if flushing is not proper. Types of servo system, two types of servo systems are there: electromagnetic, mechanical operated, and solenoid operated, and third one is hydraulically operated. Micro EDM machine, Panasonic, Japan. I will just show you the different manufacturers machine for micro EDM purposes. You can see over here, this is the Panasonic of Japan. EDMM systems, some other manufacturers are as AG Switzerland, Aurora Micro Machine Incorporation USA, Panasonic Japan, and Micro Tools Singapore. Micro machining machine, conventional plus EDMM, both operations can be done. Conventional micro machining can be done as well as electric discharge micro machining can be done, and this is DT 110. Here micro turning can be done on this machine itself. This is the micro turning tool and this is the workpiece. You can do the micro milling, this is the micro tool and this is the workpiece, and milling operation by giving the X and Y motion to the tool can be done. On machine, measurement can be done of the different features that have been machined. This is the micro EDM process. Here micro tool is there and dielectric flushing will take place and you will get the micro EDM process done over there. And micro wire EDM process can also be performed. This is a wire arrangement for traveling the wire, and wire size or diameter of the wire is few tenths of microns only. And then micro wire electric discharge grinding also can take place. That means grinding operation as well as wire EDM both are taking place simultaneously. Process parameters and micro tools fabrication. Fishbone diagram of parameters of EDMM and EDM process. Some parameters we have discussed. It gives the overall idea of the different parameters that affect the process. Let us just see them carefully. Dielectric and flushing, specific resistance, pressure, contamination, flow rate and supply method of the dielectric, all they will affect the process performance. Workpiece or electrode, diameter, material, and then what is the melting point, what is the boiling point, what is the latent heat, what is the conductivity, what is the boiling point. That is, thermal properties are very important for the tool material as well as workpiece material. Both are very important. And then you have the control strategy, melting and boiling, discharge control circuit. You can have the transistor circuit, you can have the RC circuit depending upon your requirement. Then processing, electrode rotation, discharge current, electrode may rotate, may not rotate depending upon your requirement, spark gap, capacitance, resistance, T on time and T of time, polarity and gap voltage, whether polarity means whether tool is positive or tool is negative, and gap voltage. So, these are very important process parameters for any EDM and EDMM process. Copper tool yields better surface than brass, because in some applications we use the brass as the tool as well as the copper as the tool, and we found that copper tool was yielding better surface finish than the brass. Polarities are different in two cases. Relative electrode wear in case of brass is greater than relative electrode wear in case of copper. For positive relative electrode wear, metal by you have positive relative electrode wear, because in case of cathode or the tool, whatever material is being removed from the anode, that is the workpiece, part of it may get deposited on the tool. So, metal deposition may take place, and then the relative electrode wear may be positive rather than negative, and no explanation is available, still no satisfactory explanation is available why relative electrode wear in case of brass is more than relative electrode wear in case of copper. Use of water in place of mineral oil as dielectric has shown improved performance. You can see here tool workpiece wear rate, tool upon workpiece wear rate. So, tool upon workpiece wear rate is very high in case of mineral oil, which is not desirable, because we do not want tool should wear out, but in case of mineral oil it is very high as compared to the tap water over here. So, nowadays many researchers and industrialists, they are trying to shift from mineral oil to some other dielectric, say closer to tap water or so that performance is better. Comparison of EDM performance while using water and mineral oil as dielectric, this has been taken from certain source. Now, use of solid conducting particles in dielectric, some experiments have been done just to see the effect of solid conducting particles in dielectric, and you can see here what they are doing while they are near to the sparking zone. They try to reduce the strength of the dielectric, and if dielectric strength is reduced, then definitely material removal rate will decrease, because the strength of the spark will decrease, because breakdown will take place at lower voltage. What we have done in this lecture so far: micro EDM electrodes, properties of micro EDM electrode: high electrical conductivity, high thermal conductivity, high melting point, low cost and easier manufacturability. These are the desirable properties of the electrode. Now, electrode type: metallic electrode, non-metallic electrode, combined metallic and non-metallic, metallic coating on insulator, etc. Then material used: copper, tungsten, brass, alloy, etc. Graphite. Graphite is electrically conductive, but it is non-metallic. That is why you have non-metallic electrode graphite. It is quite commonly used in EDM, and it can also be used in EDMM processes. Copper graphite, copper on molded plastic and copper on ceramics. So, these are metallic coating on insulators. You can use it as the electrode, because externally you are having the metal coating which is electrically conductive. It will save the cost, it will reduce the cost as well as serve your purpose. And powder sintered, fully or partially green compact. Electrically conductive, any workpiece material can be used as an electrode, that I have already mentioned to you. in case of EDM as well as EDMM processes. Micro EDM dielectric. You can use the mineral oil, I have already mentioned to you. You can use white oil or kerosene, this was commonly used. Dielectric, water, deionized water, and naphthic oil. These are all useful dielectrics in EDM, and some of them can be used in EDMM processes also. Micro EDM dielectric property is same as for EDM, but one has to optimize the parameters as well as the dielectric useful in case of micro EDM process. Air also has been used as dielectric for all green manufacturing, because this is very important as long as green manufacturing is concerned, that we use the dielectric which do not harm the environment. Some work was done at IIT Kanpur about 2 decades back on using the air as the dielectric in EDMM as well as EDM. Gap control and micro tool fabrication. Now here you can see interesting graph that these are the micro tools and this is the workpiece. Now what I am trying to show here is, this is one workpiece, this is the inter-electrode gap. Now as you move this, that means time is moving, and this is the material removal at different timings. So you can keep removing the material, and this is the micro tool. You can keep feeding the tool downward to make the micro hole or cavity. Now such micro tools which have the dimensions as few tenths of micron are very difficult to fabricate. We will discuss it, some of them, and we have discussed in detail while dealing with EDM process also how to fabricate them. Now you can see here, this is the tool, and the tip of this tool is very, very small, few tenths, say maybe 50, 60 or 40 micrometer. This is 100 micrometer, so it comes out to be few tenths of micrometer only. Now how to make these tools? Very important slide here. This is the block, this is the tool which you are making, or the wire. What you are doing? You are making this block as the cathode, this tool as the anode. You are moving this tool up and down for making the uniform, for reducing uniformly the diameter of this wire and rotating it, and dielectric is flowing if it is EDM process being used for creating them, or electrolyte is flowing if you are using the ECM process for creating the micro tools. So stationary sacrificial block is there which is used for this purpose. In some cases you have rotating, here this is stationary, here rotating sacrificial disc, this disc is rotating which is acting as the cathode, and this is 0.5 millimeter thick, and this is the tool being made which acts here as the anode, and it is rotating as well as moving up and down, so that material is being removed from this tool uniformly, and you can get finally the tool made of few tenths of micrometer. Now in the third case you have the wire which is having the, which may have the abrasive particles, or just simple wire here of 0.07 millimeter, and guided running wire. This is moving and sparking is taking place between this wire and this tool to be made, and which is acting as the anode, and it is rotating. This is also rotating and moving up and down. So this is how you can make the micro tools by using different EDM processes or micro EDM processes. And I have just mentioned to you earlier also that if you don't want to go for micro EDM for making micro tools, you can even go for micro ECM for making these micro tools, which can be used in micro ECM as well as micro EDM. Electrode is rotating and reciprocating, continuously rotating disc that I have already mentioned to you, and moving electrode and rotating workpiece, that also I have mentioned, and this was taken from this particular reference. Same study was done at IIT K. Sacrificial electrode, spindle tool electrode, step tool was prepared at IIT and you can see here different steps are there. Now, time taken and volume of the material removed, you can see for different cases. This is a low energy level 50 microjoules, 60 microjoules, 72 microjoules, and this is time taken is continuously increasing as the volume amount of material removed is also increasing. For higher removal of material, you need higher time. Here you have high energy level 500 microjoules, 720 microjoules, 2000 microjoules. Here time taken is smaller. Definitely when energy is larger, time taken is smaller. When energy is small, time taken is larger. This is obvious. You can see here. Now the problem is taper. Degree 0.1, 0.2, 0.3 degree taper angle, and this is the energy. At large energy, taper is large. At small energy, taper angle is small, which is obvious because with smaller energy, amount of material removed is smaller, and with larger energy, amount of material removed is larger. So taper is larger in that particular case. Microelectrode formed in a single spark in micro EDM. Let us see it here. This is the microelectrode formed in a single spark EDM, and enlarged view of the electrode. Here you can see. Now here, surprise you just see it carefully. The tip diameter or is around 100 nanometer. It is showing radius is around 100 nanometer. So you can see extremely fine tool tip is being prepared, and this is taken from Journal of Material Processing Technology. Types of EDMM and hybrid EDMM operations. Now you can see here hybrid I hope you understand it, where more than two processes are combined together to make a single process to take the advantages of constituent processes. Say for example, if you see here micro EDG, here electric discharge machining and grinding, both processes are combined together to take the advantage of EDM as well as grinding, or EDMM as well as grinding. Micro electric discharge diamond grinding, here in place of normal abrasive particles in EDG, here diamond as abrasive particles are used as abrasive, and this is known as micro electric discharge diamond grinding, where EDM and diamond grinding both are combined together to take the advantages of both the processes. And micro wire EDG, again wire electric discharge machining and grinding both are combined together to take the advantage of both the processes. ED micro sinking, ED micro drilling, ED micro milling, and wire electric discharge micro machining. All these different types of operations can be performed. Now please be careful, when I say operation, it is not the process, it is the operation I am talking about, and processes are different. EDM is a process, but sinking is an operation, drilling is an operation, milling is an operation. So spark machining method or EDM plus EDMM are used for machining complex shapes. There is no constraint of machining complex shapes if and only if you can make the tool of the approximately replica of that particular inverse replica of that particular complex shape. And difficult to machine material, they can be easily machined by EDM process, but they should be electrically conductive material. That is the only constraint. Otherwise hardness, thermal properties, magnetic properties, etc. of the workpiece material do not affect the performance. EDM, EDMM operations, you can, I have some of them I have already told you. Sinking operation, wire EDM process, micro EDM milling, as you can see here milling is taking place, and micro wire EDG, this is the wire, micro ED drilling is here. So different kind of operations can be performed at macro level as well as micro level using the EDM process. Electric discharge micro sinking operations. Tool electrode has negative shape, approximate inverse replica of the desired finished part. Please note it carefully, I am using the word approximate inverse replica, because exact replica you cannot get unless you go for thorough tool design, keeping in view the machining conditions, tool material, workpiece material, dielectric conditions and so on. Any cross sectional hole and 3D cavities can be produced by up and down movement of tool electrode along the Z axis. Micro EDM machines are available for fabricating 5 micron hole in metals and alloys. So, this is I think very small dimension of the hole being produced, that is the 5 micrometer. Aspect ratio, that we know already, depth over diameter for micro hole under 100 micrometer hole size, with 5 with kerosene dielectric, 10 with deionized water and 15 with when vibration is applied to the tool. So, you can clearly see that the type of the dielectric you are using, that is affecting the performance of the process. EDMM operations, you can have ED micro drilling. The micro electrode is rotated to drill holes with minimum out of roundness. This is very important, because your final size of the hole will depend upon how much you have the out of roundness on the micro tool, and RPM of the tool electrode is around 4000. This can vary depending upon your requirements. Machining rate with rotation increases 2 to 5 times as compared to without rotation. So, this is another very important point to note, that if you are not rotating the tool or the electrode, then the machining rate will be low. If you are rotating it, it can be as high as 2 to 5 times without rotation. 20 to 30 seconds are enough for a 30 micrometer diameter hole in 150 micrometer thick stainless steel plate. ED micromilling, simple electrodes such as round or rectangular sections, they are used, and this you can call as layer by layer machining. It is different from layer by layer manufacturing or fabrication or deposition for additive manufacturing. Used for making 3D micro shapes. CAD/CAM systems are used to generate the tool path in case of CNC machines. Now, you can clearly see here, this is the tool path along XY direction. Tool path along XY direction, cutting angle 90, this is for 0 degree. Now, in this direction you are moving, here either in this direction or in this direction, while here it is 90 degree direction with cutting angle. So, you are moving like this or like this. So, this is in different ways you can perform the milling operation by moving the tool in X and Y direction the way you want to machine it. Wire EDMM, wire diameter varies between 10 to 15 micrometer. Wire material normally used is tungsten or copper. Shape range is same as conventional wire EDM. T-shaped, X-shaped sections with width of around 50 micrometer is used. Micro gear can be cut by wire EDMM process. Electric discharge micro grinding. EDM with grinding like motion of the electrode. Rotating disc type of tool electrode is used. Slots 60 micrometer wide and 900 micrometer deep can be produced by this particular process. EDDMG, electric discharge diamond micro grinding, can also be used. Here diamond abrasive particles are used in place of normal abrasive particles being used. Metal bonded diamond wheels are used to increase the machining capability of micro EDDG. Slots can be produced with better surface finish and at faster rate. Magnetic field assisted micro EDM. With the magnetic field assisted EDMM process, a hole depth of 1177 micrometer can be achieved in tool steel. This is 26% higher when compared with the conventional micro EDM process under similar working conditions. No significant difference is noticed in the sidewall surface roughness values in the two cases, without and with magnetic field. This is very important because here a new idea has been proposed of using magnetic field to assist the EDM and EDMM processes. So far we have discussed about the basic principles of EDM and EDMM processes. Now I am going to discuss about the applications of electric discharge micromachining and some theoretical analysis of electric discharge micromachining. Thank you very much.